Okay, good morning. Today is July 19th. Okay, Viva Guayaquil. Today we are going to solve the basic problem, okay? The basic problem in this area is a simply supported plate, okay, with a load which can be represented as a sinusoidal load, okay? In that case, we can solve completely, okay? And you will see why, because we can propose a function which satisfies all boundary conditions, all. And then, since we have a sinusoidal loading, the equilibrium can be also solved with a sinusoidal function for W, for the deflection. So that solves completely. And then in the second part of the class, we can use this in order to build more complex situations. Okay, so that's the idea for this morning. Okay, and at the end, I'm going to say a couple of words about the assignment so you can start working right away. Okay, so but before that, I ask you to review material, right, for today's session. So we're going to do a poll. Okay, so I'm going to post it, and so you have to complete it as soon as I can. Okay, so we're going to go. Okay, please, I hope you can see the poll. Can you see the poll, people?
Yes, doctor.
Okay, please, let's use 10 minutes to complete it, okay? It's about plate bending, or not specifically. It's about this plate bending under sinusoidal load. Okay, so please use 10 minutes to complete it. Please read, okay? First, what are you going to do? Mr. Tanamea, what are you going to do, Mr. Tanamea? Mr. Tanamea, can you hear me?
Yes, doctor. Good morning.
What's the first thing that you are going to do, Mr. Tanamea? Read. Okay, read. Really read. Then think. And finally, answer. Read, think, answer. Go on, please. 10 minutes. Andy, from now until the end of the quiz, we are not allowing anybody to come in because otherwise they will not know what they should do, okay? After completing the quiz, yes, you can allow other people to come in. But right now, no. Okay. More than 30. Okay, time is up. I'm going to end the poll. Okay, Andy, would you please let the other people to come into the session?
Okay, doctor.
Okay, people. First question. The following expression. Let me share a screen here. Okay, can you see my white? Can you see what I'm writing?
Yes.
Okay, thank you. So this is our plate. This is X direction. This is Y direction. Please be certain that X cross Y give you Z, positive downward. That's our reference system, okay? Now, in this direction, that's the dimension A. This is dimension B. Okay, this is the origin here. Now, it tells you that we have a function W, okay, xy is equal to W times 1 minus cosine of x over A, 1 minus cosine pi y over B. Okay, now, if you try to draw this function just in the x direction, okay, just in the x direction, okay, so let's suppose this is x, okay, this is z, okay, so this dimension is A. In the x direction, you have the dimension A. Let's draw this function, 1 minus cosine, okay, cosine is like this. This is the cosine. Here we have the negative of that, so it's like this. This is minus cosine. So this is minus cosine. And then we have to add it 1. So we have to take this up to here. So we're going to have something like this. This is 1 minus cosine of pi x over A. Okay, what does this tell you? These Mr. Cedeño.
The boundary conditions are 0.
Okay, that the deflection is 0. But not only that, what else tells you that? What can you see from there? Mr. Carranza? Any other thing? Pardon me?
Complex. Deflation.
Clamped. Yes, yeah, it's clamped because you see that the slope is null. So no deflection and no slope. That means that this edge and this edge are clamped. You see that in the other direction, in the y direction, is similar. So the answer is going to be all clamped. If we can use this, we can try. It's not that easy. We can try to solve an all clamped plate in all the rectangular plate, in all the edges. Okay, that's the correct answer. Okay, let's go to the next one. We have a function that it's like this. Wxy is equal to an amplitude, and then we have sine 2 pi x over A times sine pi y over B. Okay, so again, it's the same plate. Okay, we have a plate like this. And in this direction, we measure W. Ms. Santos, what is the maximum point? Ms. Santos?
Yes.
Where do you think we have?
At the middle.
At the middle? Here? Mr. Tenamea, do you agree with that? Mr. Tenamea?
Doctor.
What do you think is the maximum value for this function?
In the A over 4 and B over
Here.
2. Yes.
Yes, I agree with you. Remember, we have to be careful with this. That means that from 0 to A, we have one cycle. And on the contrary, with this, from 0 until B, we have half cycle. You see that if you increase X from 0 to a, this angle will increase 2 pi. That's one cycle. And here, if you increase from 0 to b, this will increase pi, which is half cycle, right? So if we draw the function here, we're going to have one cycle in the x direction and only half cycle in the y direction. So the function will be something like this, downward, it will go up, and like this. So we have one full cycle, as we are saying here, in the x direction. And in the y direction, we have half cycle. So this is going to be like this. It's going to be like this, half cycle and half cycle here. So here we will have the maximum. Okay. This is something which is applicable in this subchapter. That's why I want you to practice. Okay. Any questions about that? Any problems? Anything? No? Okay. Let's go to the third question. We have a rectangular plate. A is larger than B. So in this case, it's a rectangular plate. And in this case, A is larger than B. This is typical of our situation, okay? The load is P of XY. Remember, this is force per unit area is equal to a value, P. So this is like the amplitude. And then we have sine pi x over A, sine pi y over B, okay? And what do you think is going to be the maximum bending moment? Okay, now let's draw. This is our plate. This is A and this is B. Obviously, A is larger than B. Okay, so this is the load on the plate, right? So we have, remember, this is positive. So we have, go from here, you see that this is half cycle from 0 to A. And also this is half cycle from 0 to B. So the load will be something like this. That's going to be the load. So if that's the type of load, of course, we expect the largest bending moment will be in this area. And that's the center. Okay, that's something that we want to emphasize when you have to analyze the result from the test. Okay, when you have a simply supported plate, usually around the edges, okay, since the bending moment are 0, because this is a boundary condition, the stresses are very small. On the contrary, around the central area, you have the largest deflections and the largest curvature. And since you have large curvature, you can expect to have large bending moment. Okay, so that's typical of the simply supported plates. But we have to be careful because it is possible that in some cases you have a very high concentrated forces away from the center, and it is possible that around that point where you apply the concentrated force, it is possible that you may have large stresses. But in this case, that's the shape of the load tells you something, right? And that's something that it's the central part is the most important. Okay, last question. It was similar to this case, right? And in this case, the idea was that you recognize that which one is mx and which one is my. Okay, so we have something like this. This is x, this is y. Question for you people. this moment here, this is mx or my? Ms. Arechua, what do you think? This moment here is mx or my? Ms. Arechua?
In this is my.
Ms. Dominguez, do you think it's mx or my?
Good morning, doctor. Hello.
What do you think? mx or my? What do you think?
This is a mix.
X? Yeah, I think it's mx. So this case is mx. Okay. Now, in this case, it's something which is very, I'm going to draw, I'm sorry, a very large plate like this. Okay. So let's analyze the central region. Okay, so let's do this like this. Okay, it's simply supported on all the edges. We're going to insist on this in a minute. Okay, so let's suppose that we have a certain deflection in the central part of the plate like this. Okay, now let's draw two curves with the deflection, okay, passing through the center of the plate. So if we draw in this direction, this is direction X, and this is direction Y. Okay, let's draw something like this. And now let's draw another curve in the Y direction. So we go like this and end up here. The question is, which one has larger curvature? This one here, so this is going to be WXX, or this one here, WYY. Which one has larger curvature? Mr. Chin, what do you think? Which one has larger curvature, WXX or WYY? Let's see, the curve A or curve B? Which one has larger curvature, Mr. Chin?
The curve A.
No, curve B. See, remember what, let me draw in another page, okay? What we're doing, okay, is this, okay? Let's suppose that we have a dimension from here to here. That's dimension A. Okay, and we have this is the deflection. So this is like the curve, right? So this is the radius of curvature in the Y direction, in the X direction. Now, let's draw, let me change color. Now let's draw another curve with the same deflection here, but with lower dimension. So this is B. So the curve is going to be like this. And in this case, the radius of curvature is going to be something like this. Since Ry is smaller than Rx, that means that WYY is larger than WXX. Okay, remember, this is the inverse of that, approximately, okay, because we assume that WX is small. And because of this, that means that, remember, MX is equal to minus D WXX plus nu WYY. Okay, so this one here, which is smaller in this case, okay, is here. And the other one, WYY, it's multiplied by nu, which is a small number in general. On the contrary, NY is equal to minus D and WYY plus nu WXX. So since this is larger, that means that this is going to be larger than MX. Okay, we're going to insist on this in a second, okay? Because that's there is like a comment that we always do. We say the stress, the normal stress is larger in the direction of the shortest side of the plate, okay? And we usually draw the plate with A larger than B. So in the direction of B, it's usually the largest normal stress, okay? The normal stress is highest in the direction of the shortest side of the plate. Okay, let's do a simple quiz. Miss Acuña. Miss Acuña, are you there, Miss Acuña? Are you in Manta or in Guayaquil?
In Manta.
Okay, from these 4 questions, how did you do? How many did you get correct?
1.
Oh man, so difficult. Mr. Llanos, how was your score?
Good morning, doctor. I have 3 corrects.
Any?
Yes, 3 corrects, doctor.
3 correct? That's a
Yes.
good one. Okay. Mr. Paredes, you have a question? Mr. Paredes, you have a question? Luis Paredes?
Yes, doctor. In one question, in the case in the plane is square, the moment depend the dimension or the function the.
That depends on the type of loading that you have.
Okay.
Okay, but in general, okay, for example, for us, naval engineering, the common case would be, for example, a uniformly load, right? For example, you have a plate and you have the pressure from the water in the bottom, for example, and you can say, okay, the pressure is uniform on the bottom. So more or less, that's the standard situation, right? And in that case, in the direction of the shortest side, we have the largest curvature. And in that direction, we have the largest bending moment. And in that direction, we have the largest stresses. Okay? So in general, people, please pay attention to this word. In general, right? We expect sigma y to be larger than sigma x in general. Okay? In our analysis, because we usually draw our plate with the largest or the longest dimension, A, in the X direction. Okay, but we have to be careful because some other authors, for example, Timoshenko, he draws the other way. He likes to use A over B less than 1. So for him, the A dimension is shorter than the B dimension. Okay? Okay, good. So people, please pay attention to this, okay? We have to review the material before the class, okay? Okay, let's go on. Let's stop this. Okay, so let's go on now with the, to review the material that you already have, at least have read. And the idea is that we can take this, I consider that as a simple brick, okay? And then we can build more complex situations using this little brick, which is the analysis of the plate, rectangular, simply supported plate, supporting a sinusoidal load. And you will see that why in a minute. Okay, so let's go on with, if I can find it here. Andy, can you see my full screen?
Yes, doctor.
Okay. There is somebody in the waiting room, I think. Here, I was thinking that in this graph, okay, in this graph, okay, we need to include the vertical direction. So this is really X, and this is Z. And in this direction, we measure W, which is the deflection in the vertical direction, okay? So if you can make a change, a correction in your class notes. Okay. That's the, remember here, the definition of bending moment. We use bending moment per unit width. So we have to be careful with the units. This is the bending rigidity of the plate, force length units. And this is the relation of the moment with the curvature. This is the relation of the torsional moment with the curvature using or applying kinematic hypothesis and Hooke's law. We have to be careful because mxy is equal to minus myx, but tau xy is equal to tau yx. That's something which sometimes we can get confused. Then the next step is equilibrium, summation of forces equal to 0, summation of moments equal to 0, and in the other direction, summation of moments. And then what we do is we can replace here from this expression, we get qy. From here, we get qx, and we replace it in the first one. And this is the equation for equilibrium of an element in the plate. If we had a statically determinate case, we could use this expression in order to solve the problem. Okay, but usually don't have it. So we need to combine equilibrium, which is this, with the expressions for the bending moment, torsional moment as function of the curvature. We replace this into here, and then we have a higher order equation. This is the equation, okay? And in this case, we have both equilibrium and also we have something extra. So we can use it in order to solve for statically indeterminate cases, okay? This is very important. It's partial. So you see that this is different than D. Linear, so we can superimpose partial solutions, and that's what we're going to apply. Constant coefficients, so that means that we can use exponential functions. Fourth order, that we need two boundary conditions for every point along the edges. And then it is non-homogeneous because this term here is different than 0, okay? So this is not a principal value problem. It's a common non-homogeneous problem. And sometimes we express all of this as this with this expression, nabla 4 of the deflection, okay? Just before we leave this, please give me the units of this term. Units of this term, nabla 4, people. Anybody? Units of this term, nabla 4.
1 over length to the cube.
Yes, yes, because here, that's something which is very, we have the W to the first power. And here we have the length to the fourth power. So it's like having length over length to the 4. Okay, we cancel, we get 1 over length cubed. And D, we said that has units of F, L. So we got F over L squared, and those are the units of P. Remember, P is load per unit area, okay? So people, please be careful. That's something that I have insisted a lot. Units, 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 units. Okay, the normal stress distribution, we have these two expressions for the bending moment and for the normal stress. So we can replace the parentheses expression or part of the expression in the other relation, and we can relate sigma and bending moment. Okay, so this is an expression that it's useful. Okay, so try to keep it in your memory. Okay. So let's go on. This is something that we have here. typical boundary conditions. This is, today is July 19th. Okay, so we have simply supported case. So in this case, remember, this is plate theory, so we have to be careful with the directions. Okay, so in this case, the edges don't move. So W is 0. Okay, because you have a support and the plate is on there. You can do this, but you cannot move vertically because the support is there. So in every point along the edges, W has to be 0. Okay, that's one thing. The other thing is that if remember, that's similar with what we work with beam theory. Okay, in beam theory, when we have something like this and we have support here, we said if this wants to rotate, okay, you apply a load here, this rotates. Okay, so there is no opposition to rotation, right? That means that you can do this and the support will not tell you anything about rotation. Okay, similarly in this case, in the case of the plate, but we have to be careful because we have two directions. Okay, so let's go. So let's consider, for example, this edge here. Okay, so we have a line like this one here. And let's suppose that we apply a force like this. So this line will try to rotate in this direction. Similarly with this case, if it tries to rotate in this direction, there is not going to be opposition to that rotation. Okay, because there's just support in there. You can do this without any opposition from the support. Okay, that means that there is no opposition to that. Now, this is, what slope is this? dW of what? dy or dx, people? Ms. Dominguez, can you tell me this angle here, this rotation, is dW dx or dW dy? This angle here. Is dW with respect to x or to respect to y? No?
Respect to X.
Exactly, it's the x, because we are moving in this direction. Right? Now, if that's so, okay, I'm going to draw with a different color. Let me change color. Now comes the point. This guy here, this is mx or my? Mr. Dominguez, what do you think? Is this mx or my?
My.
No, it's mx. This is mx. Okay, we have to be careful. Remember, mx, you have your finger, your thumb in the direction, in the y direction. And mx, this is the case, right? Put your finger, your thumb, okay, in the direction of y, in the y direction, and you do this. That's mx. Okay, when you go in the other direction, your thumb is in the x direction, that's my. Okay, so that's mx. And if we analyze, because we have to analyze the other also. Okay, this is going to be my. Okay, both have to be 0, but on different edges. Okay, so in the case that we're analyzing, mx has to be 0 because it is supported, and if it tries to rotate, there's going to be no opposition from the support. So on this edge, that's x equal to 0, mx is going to be 0. In the other edge, in that case, y is equal to b. Okay, again, in that case, my has to be 0. Okay, so we have to be careful because that's something that we just said. In every point on the edges, we have to have two boundary conditions. Okay, so If this is mx, okay, if this is mx, this is the expression that we just deduced, okay, this is mx, and this has to be 0 along these edges, and along this edge, I'm sorry, okay, along this edge. In that case, you see that along this edge, since this is simply supported, W is going to be 0. So if I move in this direction, okay, in every point along this edge, W is 0. If we're moving in the y direction, that means that the slope is 0 because it's horizontal line, because it's supported. So if W comma y is 0, its second derivative is also 0 along this edge. That means that this term on this edge is going to be 0. So what we have to satisfy is, since mx is 0 along this edge, we have to satisfy is that the second derivative along this edge with respect to x has to be 0. Okay, so that's something that we're going to be applying in this subchapter. So edge, this is going to be 0. Okay, so on this edge, we have W equal to 0 because it's simply supported. And also, in this case, W comma XX has to be 0. Okay. Any questions of people? Any questions about this? Okay, so along this edge, is 0. It's a straight line because we have the support. So along this direction, that's the y direction, W comma y is 0 in every point. So W comma y is 0, you differentiate one more time, W comma YY is also equal to 0. That's why we say this is 0. This H, we have two boundary conditions. Support, so no deflection, and also after simplifying this, the second derivative had to be 0. Because the D, it's never 0. So the only choice that we have is that the second derivative. So we have these two conditions along this edge. And since this is similar, also about this edge. Okay? People, question, what would be the boundary conditions on the other two? What would be the boundary conditions along this edge? Of course, W is going to be 0. What's going to be the other one? What's going to be the other condition?
Moment equal to 0.
MX and
Yeah, but
MY is 0.
please remember, this is plate theory. If you say bending moment is equal to 0, I'm going to cross you, I'm going to give you 0. Why? Because we have two moments.
MX and MY is 0.
No, no both, just one. Which one is 0 here along this edge?
MX.
Exactly. No, along this edge, MY has to be 0. Along this edge, MX is 0. Along this edge, MY is 0. Along this edge, MY is 0. Along this edge, MX is 0. So here and here, MX. Here and here, MY are 0. So that's one boundary condition. And the other is that there is no motion in the vertical direction along these edges. Okay, so as a result, we can do something similar to this. We can say that W YY is equal to 0. So we have that along this edge and along this edge, we have these conditions. And along the other two, we have these conditions. Okay? People, please If you say moment, bending moment, that's not enough. This is plate theory. You say sigma, that's not enough. You have to say sigma x or sigma y, mx or mmy, qx or qy, because we have two choices. This is plate theory. The two directions, x and y, are equally important. Okay? That's something that we just explained a few minutes ago. In the case of the clamped, plate, okay? We have to be careful because we have to consider the directions. Clamped, again, W is equal to 0. But now, remember, if you have a beam, okay, this is clamped, okay? If we have a load here, the deflection is going to be 0 here. But not only that, what's the other part of the condition, Mr. Gomez? In the case of the beam, in the case of the clamped beam, what was the other condition? Mr. Gomez?
The clamping.
No.
The angle is 0.
The slope is 0, yes.
Slope.
So the deflection will be something like this, horizontal here, and then you can start deflecting downwards. So here we have no deflection and no rotation. Now, that means that if you try to rotate, the support will generate a moment. Okay, so the moment that is being generated by the support has to be calculated as part of the analysis. Okay, now, the only thing here we have to be careful is the directions. Okay, so here we have this direction, this rotation, this is the dw, dy, and this is the direction, dw, dx. So since this is clamped, so the condition would say that this is equal to 0 and this is equal to 0. So along the edges, the deflection is 0 and the dw dy is going to be 0 on the this and that. That's going to be this. And in the other directions, in the other edges, I'm sorry, we're going to have this and that edges, we're going to have this condition. We have to be careful. It's not only the slope, it's the slope in the X or Y direction. If you say the slope is 0, that's not enough. You have to say in what direction you have the derivative. Questions about these people? Questions about this? Questions? No. Okay. Now let's use this in our analysis. So we're going to go and analyze simply supported plate, right? All along the edges, rectangular. So we have two dimensions, A and B, right? And the load is going to be sinusoidal. This very particular type of loading. So this is our plate, okay? This is our plate. And you see that we usually draw the X dimension A, the Y dimension B. And usually we work with A larger than B. Okay, that's the common situation. Now, in this case, the load is going to be like this. Okay, and that's going to solve many things for us. You'll see. So this is a constant. Okay, and these M and N are integers. Okay, and you see immediately that M is the number of half cycles of the load in the X direction. N is the number of half cycles in the Y direction. We just practiced this in this poll a few minutes ago. Okay, now We just review it. Okay, we have two edges four edges, sorry. And in every edge, in every point of the edge, we have to have two boundary conditions. Okay, so I'm going to keep, let me go back. So this and that are this. You see that this edge is y equal to 0, and this edge is y equal to b. Okay? So in this edge, this is my. This moment is also my. And in the other edges, let me change color. Let me put green. Okay, we have this edge. So these edges are x equal to 0 and x equal to a. Again, the deflection, of course, has to be 0 because it's simply supported, but we have to be careful with the bending moment. So this is mx, and this is also mx. So in every point along the edges, we have two boundary conditions: deflection, bending moment. In the x-axis, we have my. In the y-axis, we have mx. Okay? So please be careful with that. Now, of course, if the loading has this shape, we can easily expect, since the equation is linear and constant coefficient, we expect the solution to be exponential. One type of exponential is the sinusoidal. So we can say that we can expect, okay, the answer, the deflection, to have the same shape as the load. Okay, makes sense, right? Makes sense. So we expect the deflection to have the same shape as the load. So what we can do is we can replace function, okay? We can replace this function in the solution, in the differential equation for the equilibrium. So the right-hand side, you see that I have replaced by this function. This is the loading that we have. Now, because of this is the shape of the loading, we can expect to have the same shape in the response. So we can replace this into here, and as a result, we're going to have on the left, on the right-hand side, we're going to have this term. So we can cancel on both left and right. And from there, we can deduce an expression for WMN. It's very simple. You see that it is specifically the case where we have the solution is easy to find. That's why we take this as like a brick, right? And we can use this brick to build more solutions to more complex situations. Okay, people, let's take a break. It's 8:07. We're going to take 5-minute break, okay, so we can stretch our legs. Okay, you can stop the recording, Andy.
Yes, yes, doctor.
Okay, so 5-minute break, people.